Evaluating graphing piecewise functions. First, we're going to do the warm-up. So for this warm-up, go ahead and complete it on your own, and then when you're done, you can unpause the video and we'll look at the answers. So given each function below, we're going to evaluate the indicated values. So we have f of x, g of x, and h of x. So those are our functions. So for a, this is, remember, is our function notation. We are doing f of 2, which means we're plugging in x value of 2 into the f of x equation. So when I do that, I get 3 times 2 minus 2. So again, I'm just plugging that 2 in for x into the equation and then following the order of operation. So 6 minus 2, which gives us 4. So the answer to this is 4. Looking at the next one that I have, g of negative 2. So now I'm using the g of x function. So everywhere there's an x, I'm plugging in negative 2. So this is negative 2 squared. Remember, when you're squaring a negative, it becomes positive. So that means that this is equal to 4. Now we're looking at h of x, or h of 0, so h of x function. So 1 over 0, remember we cannot divide by 0, so this is undefined. Looking at the next one, we're doing f of 2 plus g of negative 2. So we already have those answers from our previous ones, A and B. So this was 4, we said, and we are adding that to g of negative 2, which was also 4. So 4 plus 4 is equal to 8. The next one we have is g of 3. So we're plugging 3 into our g of x function and squaring it, which is 9. Then for this one, notice that that 4 is not on the inside of our function notation, it's on the outside. So that means that we're taking 4 times our answer of g of 3. So g of 3 we just said was 9, so we have 4 times 9, because that's what g of 3 is equal to, which is equal to 36. Looking at the next one, we have 2 times f of negative 1. So in this case, f of negative 1, we need to figure out what that's equal to first. So when I plug in negative 1 for x, I get 3 times negative 1 minus 2, which is negative 3 minus 2, which is negative 5. So then we have the 2 times that answer. So 2 times negative 5, which is equal to negative 10. So now let's get into the actual lesson. So piecewise functions. If we want a function to behave differently depending on the x values, we need a piecewise function. A piecewise function is just a function that uses more than one equation to describe its behavior. When we graph piecewise functions, we are really graphing different pieces of different lines. So a piecewise function is a function defined by 2 or more equations. Each piece of the function applies to a different part of its domain. An example is shown below. So if you look at this example, this right here is the piecewise function. So notice we have f of x equals 2x plus 1, and it tells us x is greater than 0. And then underneath that, we have x minus 2 for x values less than or equal to 0. So these are the domain restrictions, and they tell us where we are starting our x values on our graph. So notice if we look at the graph to the right over here, the first equation on the top, f of x equals 2x plus 1 is greater than 0. Notice that we don't have any of the values less than that, which is greater than 0. And because it's greater than 0, not equal to, that's why there's an open circle here at 0. And then for this one, it's less than or equal to 0, which is why this is a closed circle, and we have values of x that are going the other direction. So that's what we are looking at when we're talking about graphing piecewise functions. So let's go ahead and do some practice of these. So before we actually graph them, let's look at evaluating the piecewise function given the values of the independent variable. So we have two functions here. We have f of x and g of x. So for the first one, let's go ahead and look at f of 0. So f of 0 means we're using this function right here, f of x. So 0, in order to know which equation to use, I have to look at my domain restrictions. We look at the first one, is 0 less than or equal to 1? Yes, so that means we're going to use that top equation. And you can check the bottom one too. 0 is not greater than 1, which is why we're not using the bottom one. So we have 3 times 0 minus 1. So that's 0 minus 1, which is equal to negative 1. Looking at the next one, we have f of 1. So again, we want to look at the domain restrictions. Is 1 less than or equal to 1? Yes, it is, so it goes into that top equation. 3 times 1 minus 1, which is 3 minus 1, which ends up giving us 2. For the next one, we have f of 5. So we go over here. Is 5 less than or equal to 1? No, so we're not using that top equation. Is 5 greater than 1? Yes, so now we're using the bottom equation. So 1 minus 2 times 5. So that gives us 1 minus 10, which is negative 9. So why don't you go ahead and pause the video and see if you can do the rest of the equations, and then when you're finished, unpause and we'll take a look at your solutions. So the next one we have is f of negative 4. So negative 4 is less than or equal to 1. It's less than, so that means we're using the top equation here. So 3 times negative 4 minus 1. So that gives us negative 12 minus 1, which is negative 13. For the next equation, now notice it's g of 0, so that means we're going to be using this piecewise function. So we have 0, and we want to look at our domain restrictions to see where our which function we're going to plug it into, the top, middle, or the bottom. So if I look at 0, is 0 less than or equal to negative 3? So for this one, remember negative 3 on the number line is going to be lower than 0, so it doesn't fit into this top equation. Negative 3, and then we have 1, so x values in between negative 3 and 1. So 0 in this case does fit in between negative 3 and 1, and it's not greater than 1. So we're using this second or middle equation. And so if you look over here, notice that there is no x value. It just says g of x equals 2. That's the portion that we're looking at. So for g of x equals 2, if you think about this as a graph, on a graph, what does that mean? This means we have y equals 2, and remember that's a special graph, so that's a horizontal line at 2. So it would look like this. So that means no matter what x value you're using, your y value is always going to be 2. So for this problem here, that means if I have g of 0, the answer is equal to 2. Looking at g of 3, negative 3, excuse me. So looking at negative 3 is less than or equal to negative 3, so that means we're using the top equation. So 3 times negative 3 minus 1, which gives us negative 9 minus 1, which is negative 10. Looking at the next one, g of 1. So 1 is not less than or equal to negative 3. 1 is not in between negative 3 and 1 because, again, this doesn't have an equal sign. So the bottom equation, 1 is greater than or equal to 1. We're going to be using that one. So negative 3 times 1, which is negative 3. For the next equation, we have g of 3. So g of 3 means that we're not using this bottom equation because 3 is not less than or equal to negative 3. It's not in between negative 3 and 1. It is greater than or equal to 1, in this case greater than 1. So we're using the bottom equation, negative 3 times 3, which is negative 9. Negative 5, in this case, would be in using the top equation because it's less than negative 3. So in this case, we have 3 times negative 5 minus 1, which gives us negative 15 minus 1, which is negative 16. Looking at these last two, we have f of 0 plus f of 1. So we already did that earlier. So this was our f of 0 equation. This was our f of 1. So we're just adding those two answers together. So negative 1 plus 2, which gives us 1. For the next one, we have 4 times f of 0 plus 3 times f of 1. So f of 0 we just said was negative 1. So 4 times negative 1 plus 3 times f of 1, which is 2. And then we're just simplifying this. So negative 4 plus 6, which is equal to 2. So that's evaluating piecewise functions. Next, we're going to look at graphing piecewise functions. So these are the steps that I like to use when graphing. So step 1, identify how many pieces and the type of function. Step 2, graph the functions using the transition points as beginning and ending values. Step 3, use open or close points to indicate the correct domain of each piece. And step 4, check your piecewise functions graphs. They should not cross each other. So keep that in mind when you are graphing these. So looking at the first part, if I look, I do want to do step 1, identify how many pieces and function type. So if I look here, there are two different pieces. We have this top equation and the bottom one, and both of these are linear. So we have two equations, and they are linear. Then it says graph the function using the transition points as beginning and ending values. So if I do that, we're going to go ahead and look here at this first equation. So we have x values, and then our y values are equal to 2x minus 1. So that's what we're going to be plugging it into. So now look at your domain restriction. This is for x values less than or equal to 1. So if it's equal to, that means we can use a closed circle on our graph. And so we can actually start with 1. Then we would want numbers less than 1. So 0, -1, etc. So if I plug 1 into this equation for x, the top equation, I get 2 times 1 minus 1, so 2 minus 1 is 1. If I plug in 0, 2 times 0, 0 minus 1 gives us minus 1. If I plug in -1 to the top equation, 2 times -1 is -2, minus 1 is -3. So on my graph, I'm going to start at my domain restriction, which is an x value of 1. So at my x value of 1, I have a y value of 1. It's a closed circle. Then the next point I have is 0, -1, and then -1, negative, 0, -1, and -1, -3. And now I can use my ruler to draw the linear function. So now I've graphed my linear function, it's just a straight line. And for this, I can now go ahead and start working on the other equation. So the other equation, we have x and y is equal to -x plus 3. Now again, even though we are using this domain restriction, because it's not equal to, we're going to use an open circle in the graph. Even though it's an open circle, we still want to put the open circle on our graph, so that's why we're going to start using that value even though it's not really included in our solution set for this equation. So 1, and then we want values that are greater than 1. So 2, 3, we could do 4, etc. So now when I plug in 1 to the bottom equation, -1 plus 3 gives me 2. -2 plus 3 would give me 1. -3 plus 3 is 0, and -4 plus 3 is -1. So on my graph, I start at 1, 2, but it's an open circle because we cannot include that. Then I have the point 2, 1, 3, 2, 1, 3, 0, and 4, -1. And then I'm going to use my ruler to connect the points and draw my straight line. And there we go. And so the reason it's really important that you use that circle right there, because otherwise if you don't put that circle there, you would be missing all these values that are in between, or I should say x values in between 1 and 2 right here. So that is why that's important. And then for this, if we want to look at the domain of our graph, the domain for this graph, you notice that we have x values from -infinity, and then 1 is the area that we're concerned with, but this closed circle means that we are including 1, and so it's going to infinity, so -infinity to infinity. And that is our piecewise graph. So let's go ahead and do another one. So for this next one, we have g of x equals negative 4x for x values less than or equal to 0. So let's go ahead and start with that one. So if we start with our domain restriction, we have 0. And for this, you notice that, which I forgot to say at step 1, these are two equations, and they're both linear. So for this, if we start with 0, we have x values less than 0. So the next value that we're going to go ahead and graph would be negative 1. And then we could do negative 2, but negative 2 is not going to be on my graph, and you'll see why in just a second. So when I plug 0 in for x, I get negative 4 times 0, which is 0. Negative 4 times negative 1 is 4, and negative 2 times negative 4 is 8, and so I didn't actually make my graph large enough for the 8. That's why it's too big. So if I graph this, this top equation is using a closed circle. So at 0, 0, we have a closed circle. Then we have negative 1, 4. And we can go ahead and use our ruler to graph. And that's our line. So now if I look at the second equation, we have x and y equals 4. We want values that are going to be greater than 0. This is going to be an open circle at 0. So we're going to start at 0. Then we have 1, 2. So if I plug in 0 into this equation, because this is just equal to 4 and there's no x value, that means all of these are 4 because we have a horizontal line at 4. So 0, 4, it's an open circle, and then we want values that are greater than 0, which go this way. So the domain of this, again, is still all real numbers. Even though we have that jump in our graph, this value is taken care of right there. You can also check your other equation, the line that we have, that you plotted the points correctly by looking at the slope. So you notice that since this is linear, we know how to graph linear using the slope rise over run. So this one, in this case, we know we're going down 1 over 4, or excuse me, down 4 over 1. So down 1, 2, 3, 4 over 1, which checks our work from when we plotted the points. So then for the next one, if you want, you can go ahead and pause the video and do this one on your own and then unpause it to check your answer. So here you see we have 3 different parts. So 1, 2, 3. So 3 different parts of our graph that we have to graph. So the first one that we're looking at, we have x and then y equals negative 1. And we have values that are less than or equal to negative 1. This is a closed circle at negative 1. So values less than that would be negative 2, negative 3. This is a horizontal line, so all of these are going to be y values of negative 1. So at negative 1, we have a closed circle, and we have values that are less than that. Then if we look at the next one, we have 0 for the equation, so horizontal line at 0, but we only want values in between negative 1 and 2. So we have negative 1, 0, 1, and 2, and they're both open circles because it's not equal to. So at negative 1, I know it's going to be 0 because it's a horizontal line at 0, so these are all 0. So we have negative 1, 0, and that goes all the way to 2, 0, and all the values in between, and not including negative 1 or 2. And then the last piece that we have is x and y equals 1. So we have values of x that are greater than or equal to 2. So this is a closed circle on our graph. And so we start at 2, 3, 4, and it's a horizontal line at 1. So these are all going to be y values of 1. So at 2, 1, we have a closed circle, and our graph goes this way. So for this, if we look at the domain's all real numbers because even though we have this jump right here, this x value is taken care of, and same thing here. So negative infinity to infinity. All right, so let's go ahead and look at number 4. So for this one, again, we have 3 different pieces to our graph. So let's go ahead and look at the first piece. So this is linear. So we have x and y equals 3x plus 12. We're starting at x values less than or equal to negative 3. And I know this is going to be closed circle because it's equal to. So numbers less than negative 3 would be negative 4, negative 5, etc. So we're just going to use these two. If I plug negative 3 into that top equation, negative 3 times the 3 would give me negative 9 plus 12 is 3. If I plug in negative 4 times 3 is 12, negative 12 plus 12, which is 0. So on my graph, I have negative 3 and 3, and we know this is a closed circle. Then I have negative 4, 0, and this is linear, so I can use my ruler to go ahead and graph my line. Oops, which would go this way. All right. So looking at the next part, we have our second equation. For our second equation, this is an absolute value, so we know it should be a V shape, but because we're only graphing part of it, it might not actually look like a V shape. So we have values in between negative 3 and 3. They're both open circles because they're not equal to. So we'll start at negative 3, negative 2, negative 1, 0, 1, 2, 3. I know that this is the parent graph, so the vertex is actually at the origin. So the vertex is at 0, comma 0. We just did that the other day. So, and that's included in our solution set. So because we know that's the vertex, we know that both sides are going to be the same. So it's going to be easy to plug in those values. If I plug in negative 3, I get 3, 2, 1, 0, 1, 2, and 3. Because remember, the absolute value is the distance from 0 to a number line. And then again, I can use my ruler to go ahead and connect the dots. And so that would give me my graph. And they are both open circles on my graph. So this one, even though it's an open circle, because this graph overlaps with the graph that was in red, the top equation, that actually closed in that open circle, so we can leave it closed because of that first function. And we'll put this one as an open circle over here. So then we have our last graph, which is the bottom equation. So x and y equals negative 3x plus 12. So we want values that are greater than or equal to 3. So we're going to start with that on our table. This is closed for the circle because it's equal to. So I'm going to plug in 3 and 4 for x into my equation. Negative 3 times 3 gives me negative 9 plus 12, which is 3. Negative 3 times 4 is 12 plus 12, which is 0. So we have 3, 3, so that closed that open circle in, and then 4, 0, which would be right here, and then we can use our ruler to go ahead and graph. And so that is our piecewise function. So we had 3 different parts to our function. 2 of them were lines, and the middle one was the absolute value equation. And the domain for this is, oops, all real numbers. So negative infinity to infinity. All right, so we have our last graph. So again, you can go ahead and pause the video, see if you can do this on your own. When you're finished, unpause it to check your work. So we have 2 equations that we're looking at here, so 2 domain restrictions. And the top one we know is going to be an open circle because it's not equal to, and the bottom one's going to be closed. And so for my top equation, it's linear. And I want values that are less than negative 2, so we're going to start with negative 2, and negative 3, negative 4, and plug it into that top equation. So when I do, I get 3, 2, and 1. So negative 2 and 1, 2, 3, we know it's an open circle. And then we have -3, 2, and -4, 1. And again, it's linear, so we're going to use our ruler to graph our line. And there we go. And now we can go ahead and do the second equation. So this is x and y equals x squared plus 2x plus 3, which we know is a quadratic equation. Remember, quadratic equations make a parabola shape or a U shape. So for this one, we want x values that are greater than or equal to -2. So we start with our domain restriction, -2. Values greater than that would be -1, 0, 1, and 2. We'll just go ahead and stop there. So if I plug in -2 into my equation, -2 squared is 4, plus 2 times -2 is 4, so that cancels itself out, and then we have plus the 3, so 3. So -2, 3 means we're closing in that open circle that we had. If I plug in -1 squared, remember if you square something that's negative becomes positive, so that's 1, plus 2 times -1, which is -2, and then plus the 3 gives me 2, so -1, 2. Then I have 0. If I plug that in, I get 0 squared, which is 0, plus 2 times 0 plus 3, which gives me 3. And then if I plug in 1 squared plus 2 times 1 plus 3 gives me 6. So 6 would be up here. And again, you can see that this is the vertex, so just part of my parabola. And the domain of this is also all real numbers, -infinity to infinity. And so that gives us our last piecewise defined graph.